Hey everybody, let's talk about polar coordinates and graphs. You have seen polar coordinates once before when we did vectors. The idea is still the same. Instead of coordinates telling you an x and a y, how far over and how far up, these coordinates tell you a direction, like maybe 45 degrees, and then a distance that you go in that direction. And that's just two numbers that tell you a point in space, but they tell you it in a different way. Okay, so we'll start just by plotting some, and the most important thing to understand here is the idea of a negative distance. So, where is this one? This says we're facing at an angle of 90 degrees, so we're facing straight up, and we're going to move a distance of 3. So 1, 2, 3. So the point A would be up here. What about this one? We're facing at 45 degrees, so we're facing this direction, and we're going to move a distance of 3. You might think that I should go 1, 2, 3 to take me out here, but if you actually imagine calculating the distance along that diagonal, using the Pythagorean theorem, this is 3 and this is 3, so that distance must be, well, I mean, we don't even need to know the number. If this is 3 and this is 3, that diagonal is clearly longer than 3. So a great thing to do would be to draw part of a circle. Okay, not my best circle, but pretend that that's a circle. Every single point on this circle is a distance of 3 from the origin, because that's the radius of the circle. So now I can say, all right, 45 degrees, if I go right until I hit the circle, I know that point is at the right angle, and it has the right distance. Okay, so let's go ahead and add a couple more circles. Let's do one at radius 2, and let's continue the radius 2 one around to, well, let's just do the whole circle. Okay. So this one, 30 degrees. Let's go ahead and add, that's approximately 30 degrees. And I'm going a distance of 2 at 30 degrees. So that would be about here. So there's C. Here I'm pointed at negative 30 degrees. So that would be the same 30-degree angle, but this time a negative angle wrapping in this direction. And so the point D would be a distance of 2 if I was facing this direction. Okay, the last one. How do you think about a negative distance? So if I'm at an angle of 30 degrees, you have to imagine me facing in this direction. Like, well, if I could draw a little stick figure, I would, but here I am, facing in this direction. I'm looking at 30 degrees. But instead of walking forwards 2, if my distance is negative 2, it would make sense for me to walk backwards 2, but at that exact same angle. Ooh, my angles are getting all wonky here. Okay, let's pretend that's a better angle. So if I walk backwards 2, now I'm over here. This idea about walking backwards is going to play a really important role in understanding the interesting graphs that we can make later on. Okay, so, last thing. So let's say I have a polar equation, a polar set of coordinates like r theta. So for example, it might be like 45 degrees. If you think, wow, it would be really great to turn those into xy coordinates. You saw this once before, hopefully you remember why. It would be 2 times cosine 45, 2 times sine 45. And in general, to convert polar coordinates into rectangular coordinates, you would have the radius times cosine of the angle, and the radius times the sine of the angle. And you could go back to the vectors unit and watch that video to understand why that's true. Alright, let's look at the absolute simplest graphs that you can make with polar and rectangular. So if I'm in rectangular, like y equals a constant and x equals a constant are the simplest graphs I could make. So let's put 1 up here. If y equals 1, that of course is just the horizontal line at 1. Let's remember like what it means to be a graph though. What it means to be a graph is it's the infinite set of points that all satisfy that equation. So this line is actually just all points with y coordinate of 1. Okay, so what about this graph? So let's put 1 down here. If x equals 1, that's just all the points with an x coordinate of 1. So it's a vertical line. So this is all points with x coordinate 1. All right, so as we're going to start, and like in a second, we'll look at y equals x and the polar equivalent, r equals theta. So just like equations using x and y are asking what are all of the points that have a certain x or a y, here when we have r and theta, we can ask what are all of the points that have a certain r, or all the points that have a certain theta. So take a guess right now. If I was going to plot all of the polar coordinates here that have an r of 1, where would they be? So I could imagine, so r is the radius, but I could imagine different angles. I could imagine an angle of 0 degrees and 30 degrees and 45 and 60 and all the different angles. But what's common is the distance I go for every single angle is going to be 1. So no matter what direction I'm facing, I go out a distance of 1. So that's going to make a circle radius 1. And that's the graph of that equation. So this is all points with r equals 1. I just want to pause for a second. If you were going to make the graph of a circle using x's and y's, it's definitely not a simple equation. But with polar coordinates, it's the simplest equation you can have. So there's going to be a bunch of clues about how polar coordinates are different, and that's why they're useful. So we're going to start thinking about when would you use polar ways of thinking versus rectangular ways of thinking. And it has to do with what's simple to do with polar that would be complicated to do with rectangular. All right, what about theta equals 1? So let's pretend that this is in, well, let's pretend this is in degrees. So if it's 1 degree, you know, I'm going to exaggerate it a little bit. That's like, it's more like 10 degrees, but let's imagine 10 degrees. So all the different points along this line, all the different distances along this line would satisfy the equation where theta is 1 degree. But I could remember you can also have negative distances. So if I was facing at an angle of 1 degree this direction, but I had like -1 as my distance or -2, I'd get points over here. So that's why this equation is just a line. And so this is all points with theta 1 degree. Okay, so basic curve, like the most basic shapes in rectangular are horizontal and vertical lines. The most basic shapes with polar are circles and lines that go through the origin. Like imagine 1 was something different, like, I don't know, 35. Then it would still be a line that goes through the origin, but it would have been rotated a little bit. So let's start graphing some more interesting equations. Let's compare y equals x to r equals theta. So y equals x, no mystery there. We've been doing this a long time. But let's think about what it means. Why does it have this shape? What this equation is literally saying is, let's plot all of the points whose horizontal distance is the same as the vertical distance, whose x is the same as the y. And you can see them, I chose a couple of points right here. So what happens if we have that same relationship, but between r and theta? So I'm not saying horizontal same as vertical, I'm saying whose distance is the same as the angle. So if I choose an angle of 45, I'm going to go a distance of 45. If I choose an angle of 90, I go a distance of 90. So what's that look like? It's not that easy to imagine here. So that's why we're going to plot some. So instead of x and y, let's see, the equivalent of x over here would be theta, because that's the independent variable. That's the thing we're going to change. And then this one's going to be r, because the radius is going to be based on the angle. So it's like I'm going to plug in an angle and calculate how far do I go for that angle. So let's plot these as if they're polar coordinates. So angle 0, I'm facing this direction. Well, here, let's actually just look at the angles first. So notice that it's 0 and pi over 6 and 2 pi over 6 and 3 pi over 6. So it seems like I'm going to be going in increments of pi over 6. So why don't we like sketch in some pi over 6 angles here. So here's 1 pi over 6, 2 pi over 6, 3 pi over 6. And then here's 4 pi over 6 and 5 pi over 6. All right, so when I'm facing at an angle of 0, I go a distance of 0. So that puts me right here at the origin. So that's point A. Point B, I'm facing in this direction, and I go a distance of pi over 6. But it's not like what is a distance of pi over 6 here? Here my scale is in terms of 1 and 2. Let's call, for the purposes of our graphing, it's going to be a little approximate. Let's assume pi over 6 is about 0.5. It is about 0.5. So if this would be distance 1, distance 0.5 would be about half that. So here would be point B. You could just pause the video and go ahead and sketch the rest of these, or I'll do it too. So for C, I'm at an angle of 1, 2 pi over 6, and I'm going a distance of 1, 2 pi over 6. So there's point C. For point D, I'm going 1, 2, 3 pi over 6. That's pi over 2, so I'm facing up. And my distance is 1, 2, 3 pi over 6 distance. So there's D. Hopefully you can sort of imagine connecting these and think, where's this going? For E, it's 1, 2, 3, 4, and 1, 2, 3, 4. And for F, it's 5, and it's a little off the graph. F is kind of over here at 5. Okay, so if we imagine now connecting all the dots, they appear to be making a spiral pattern. Let's verify this on Desmos. So you can go to my little grapher at FHS PCH Polar. So I should say, actually, in Desmos, you can just type an equation in, and if you use r and theta, it will plot as polar. So I can say r equals theta, and it shows me this spiral here. So cool. But what's more helpful than that is to actually imagine the angle increasing and to watch what's happening to the radius that whole time. So let's actually go to this one. For this one, we're going to use t instead of theta. But here I'm saying, let's plot r as a function of t. And you can hit play here, and now you can actually watch it increasing. So here we've gone from an angle of 0, there we are at an angle 45 degrees, here we are at an angle of 90 degrees, and so on. So you can actually think about how it would plot, the way that you would plot it. So there we go. It is in fact a spiral, and this is how you should think about plotting all polar curves yourself. You should really imagine like this rotating angle, and then for each different angle think, how far do I go in that direction? And that's going to be the r. In class, a lot of people wanted to know, hey, what happens when we go past 2 pi? Well, let's go all the way to 8 pi and see. So back here at 0, there's 2 pi, there's 4 pi, there's 6 pi, there's 8 pi. So you do just keep going around and around. Some people wanted to know what happens if you get to negative angles. So I think my grapher actually doesn't work for negative angles, but let's see. Yeah, so I'm not actually plotting the line for negative angles, but let's go and see what happens to the point. So here I am at pi, backing up to 0, and then it's going in the opposite direction. And you could think about it yourself, like this would be an angle of, let's see, negative 45 degrees. So negative 45 degrees faces down this direction. But if I'm going a distance of negative 45, that takes me in the opposite direction, so I'm plotting up here. So you can also think about negative angles and negative distances. All right, let's close it out with one more example that's going to help you think more in a polar way. Flip it over to the back side. This is supposed to be kind of a thicker line right here. So in order to help us, let's divide, well, let's think what we're doing here. So here I have a graph in rectangular coordinates because they're all kind of xy coordinates. But let's say I was going to interpret the x coordinate as an angle and the y coordinate as a distance. And then I'm going to take every single point in this graph and plot it as polar coordinates over here. So what's it going to look like? What would this straight line turn into? What would this diagonal line turn into? And so on. So to help us, let's imagine breaking this into the 4 quadrants. So quadrant 1 is going to be between 0 and pi over 2. So here's quadrant 1. And then quadrant 2 is going to be between pi over 2 and pi. So that would be between facing up and facing left, and so on. I think it would be great for you to stop the video and try this on your own, and then we can debrief. So if you would like to do that, go ahead and do that now. I think you will learn more that way. Okay, fair warning. Here we go. So I'm going to label several points here. I'm going to call this A, and B, and C, and D, and E, and F, and G. And I'm going to start just by thinking about those points, but I also have to think about what's happening in the middle here. So A has an angle of 0 and a distance of 4. So if I'm imagining angle 0, that's facing to the right, distance 4 would be 1, 2, 3, 4. So here's point A. Point B is at an angle of pi over 2, so I'm facing up, and it's also at a distance of 4. So point B, oops, which I should have made an open circle. Well, it's too late now. So imagine B is an open circle, and it's right over here. Okay, but what's happening in the middle? I wouldn't just connect these with a straight line. So let's imagine a couple of other points. What if I had one at 45 degrees? Or what if I had, 5 equally spaced points in there? What I'm noticing is no matter what the angle is, the distance is always 4. So you can imagine several different angles here. Doesn't matter what the angle is. The distance is always 4. So I'd have points all along the outside here. So a horizontal line for rectangular coordinates turns into part of a circle for polar coordinates. Okay, what about this one? What about this line that's going towards 0? So at an angle of pi over 2, I'm at a distance of, it looks like about 1.5. So that's about here. So there's C. And then for D, at an angle of pi, when I'm facing to the left, I'm at a distance of 0. So that's actually gone back to the origin. So again, what do I do? Should I connect these lines directly? Probably not. You have to imagine what might be happening in the middle. So let's look at just 3 pi over 4, for example. So 3 pi over 4 would be 45 degrees this direction. We are at a distance of about half of 1.5, which is about 3/4. So 3/4 would be about here as a distance. So if I'm facing up, I'm at 1. If I'm facing 45 degrees over, I'm at 3/4. And then when I'm facing left, it's at 0. If you wanted to, you could imagine 2 more points in the middle. So when I'm facing at this angle, I would be about halfway between 3/4 and 1.5. So kind of here-ish. At this angle, I would be kind of here-ish. So remember, I said that you have, I'm going to zoom way in. So remember, I said you have to be able to imagine as the rotation is happening, how are the distances changing. So when it's facing up, I'm at 1. My angle increases a little bit, and my distance decreases. My angle increases, my distance decreases. My angle increases, my distance decreases. And so if you put those together, that's creating this kind of moon shape right there. Fill it in pen. So that's the kind of thinking that you're going to have to do. It's all well and good to memorize shapes, but you want to be able to think your way through new situations. And the way you're going to do that is by thinking about individual points and imagining what are the transitions looking like between those points. So in quadrant 3 here, so that's quadrant 2. In quadrant 3, I'm looking at angles between pi and 3 pi over 2. So between left and down. If you want to try this one on your own, if you haven't done it on your own yet, by all means, try it on your own right now. So D was right here. E is going to be a distance of 1.5 facing down, so it's going to be there. And this is just symmetric to that one. So in quadrant 2, I had my distances decreasing to 0. Here I have my distances increasing back to 1.5. So as my angles increase in this direction, my distances are getting bigger, 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 bigger until I get to 1.5. So this should be symmetric approximately like that. And then for this last quadrant, quadrant 4, that takes me from 3 pi over 2 up to 2 pi. It looks like all my distances are just 1. So I've got open circle here at 1, and then filled in all the way It's a closed circle there. So the horizontal line segment there became this part of a circle. This line became that moon shape. This line became this moon shape. This line became that quarter circle. So that's been your introduction to polar thinking. None of this is very interesting. This is all just kind of getting you to feel the basics. In the next couple of lessons, we'll start looking at what can you do with this stuff, kind of why is it interesting, why is it really, really different than rectangular.